measure gases, right? You can't put them on the balance. You can keep jam them in a jar as much gas as you can fit in there, so you can't really just measure by a container. What are we going to do? Well, that's what this chapter is about. It's called Gas Laws, and today we're going to learn about, first of all, we talk a little bit about how gases are, and then we're going to focus on how we measure them, and then we're going to focus how to calculate the amount of gas you have. And when we're talking about everybody's favorite, we're going to get to moles. Once we get to moles, we can go anywhere we want because we can go mole to mole to wherever. And that's our goal. All right, so let's just get started here. Chapter's a little bit different, a little bit more notey than the last few chapters. So take these notes, write these notes down as we go. This page will be a grade when we get done with this section. Not today, but at the end of this whole chapter, it'll be something you submit then. Okay? That sound interesting? I know what you're thinking. Oh, no, it doesn't sound interesting at all. But it will be. Let's do it. Okay, so first of all, before we can talk about gases, we have to talk about the kinetic theory, or the kinetic molecular theory, as it says on the paper there. Simple theory. Kinetic means motion. Molecules, right? They're particles. Molecular, or kinetic molecular theory, just says particles in motion. And all that's saying is that everything is made out of particles, and those particles are moving all the time. Simple, right? Now we could go in details, talk about solids and liquids and things like that. And we've talked about that kind of stuff over the whole year. But we're going to talk about the gases this time. So we're going to focus in on the gases. All right. Now, one thing we're going to do is we're going to take these this rule about particles in motion, and we're going to apply it to gases. Okay, now, not just any gas. We're going to make ideal gases. Ideal means the perfect gas. All right, what we're trying to do is to simplify, because if we had to take into account every teeny little thing that there was about a gas particle, its size of the molecule, how fast it's moving, how much it weighs, all that stuff, it will get too complicated. So, much too complicated, right? So we're going to keep it simple. And by keeping it simple and making some generalizations, we get very close to the truth, which is doable, calculatable, and also fun, because calculations are fun. All right, so let's talk about this first thing. Here's the 5 rules. Now, I use the term, and I'm going to write it down here. I use the term ideal, right? So ideal means perfect in every way. So we're going to make these gas particles perfect. First of all, let's talk about the size of the particle itself, right? Really, in real life, okay, this is real life. Those molecules, those atoms, they take up space, right? And so what we're going to do is we're going to reduce that down to they have no space per particle. They really do, but we're trying to make the math simpler. So just like in geometry class, when you say a point has no dimensions, it's just a spot, we're going to say the same thing about the particle sizes. They have no size. I'm making a video, dude.
I can even make your video somewhere else.
You can't. I can't.
Yeah, you can.
All right, get out of here.
Need to make your video somewhere else.
You know how I can get you out of here?
Huh.
Hey, Mommy! Franklin's bothering my video! Okay, back to normal.
Mommy! Ed is punching me really hard.
Boom!
I don't feel so good anymore, Mommy. I don't think I can walk.
All right, you're taking my whole video. These guys don't want to listen to you. Okay, so collisions. Now, when we talk about the
A
collisions...
collision is like that.
Yes, right. When we talk about the collisions of gas particles, though, we're going to say that like when Franklin hit me in the head with that computer, you could hear it make a sound, right? That was a loss of energy. We're going to say the collisions of particles, gas particles, the collisions are elastic. Now, elastic... Oops, let me get out of the way. Yeah, get that computer out of the way. Okay. So, I don't have a mouse with me. There we go. So the collisions are elastic. And elastic doesn't mean it's stretchy. Elastic means that it doesn't lose energy. Okay, so I always like to use those bouncy balls, those super balls. You drop them and they bounce really high, right? But they don't bounce as high as they originally were when you dropped them. A perfectly elastic collision, that ball would just bounce the same height forever and never stop. That's how we're going to pretend these gas molecules are. All right? All right, next one. Gas particle motion. We're going to say that they travel in straight lines. And the only way that they change direction is from bouncing off or colliding. So the only time they change is from collisions. And they're bouncing all over the place. Right? And those collisions are elastic, so they're not losing energy during these collisions. Okay. The attraction between molecules. Now, we know about polar molecules. And we talked about London dispersion forces. We know there's attraction between molecules. We know it. We know because we talked about it, right? But we're going to pretend that doesn't exist in this. It's small anyway, especially for gases, because most of them are non-polar, covalent, right? And so we're going to say that the attractions don't exist. Right? If they did exist, they wouldn't have perfectly elastic collisions, right? So we're going to say there's no attraction or repelling. I should put repelling between the molecules. I'm just going to leave it like that, okay? Because that's enough said. Okay. Now our last one we have is a little bit different. Temperature. I think we talked about what temperature was earlier this year, so this won't be that long. All right. Remember we talked about temperature, and we said it was the speed of the particles. Now, you had to take in consideration a little bit of the mass, right? And what we call that is the kinetic energy. So the temperature is the average kinetic energy of the particles. And I believe we did talk about that, so I won't say much more about it. So what we're saying is the faster the particles move, the greater their temperature is. Okay, now, I hope that makes sense. Again, this is to generalize the gases to make it easier. You'll see when we get to the problems how nice the problems are. So just hang with me. All right, let's talk about some of the nature of gases, some of the things that they can do. And you know these. You know all these probably. Well, maybe not the last one. Expansion. Gases, the particles are moving really fast. They want to spread apart, right? They can expand. They can spread apart. There's a huge amount of space between gas particles, right? If you remember from this is the old model. A solid, the particles are vibrating. Liquids, they can flow around each other. And gas particles are flying everywhere. They can be as far apart as they can get. All right? So expansions, gases can spread apart. I'm just going to put gases spread. You know what that means. I know what that means. Remember what it means, not, Okay, fluidity, right? Fluidity doesn't mean water or liquid. Fluidity means that it flows. That's all it means. So liquids are fluids. We know that. But gases are also fluids. Gases are actually better fluids, right? They flow better. So all fluidity means is that it can flow. And being from Upper Sandusky, and you go out on a nice windy day, you know that gases can flow. Low density. The particles are spread really far apart, right? So of course they're going to be low density because there's a big space, small amount of particles. Large space, small mass. Okay? Large space, small mass, low density. Compressibility. They can expand. We can squeeze them together. That's what an air compressor does, right? I need to pump up my tires of my bike back there, right? Look how low they are. Oops. Low, right? They should have about 110 pounds of pressure, and they probably have about 10, right? So we can squeeze a bunch of air into those tires. Those tires aren't going to get any bigger. They're just going to be really hard. They're going to have a lot of gas shoved into a small part. So gases can be squeezed together. The bike's not down here just for that demonstration. Oh yeah, I dragged that down here just to show you that. Exactly. Diffusion. Okay, now diffusion. Have you ever been, well, I should say it this way. If you have something that is really stinky, right? Say, usually I bring out a little container of ammonia in class and I sit it down on one of the desks and I don't say anything. And before I even start talking. And then pretty soon, the person by that is like, oh, stinks. And then the other people will be like looking at them weird, but it'll gradually spread. Say, here's the container, right? Oops. Yeah, there it is. So here's the container right here. And it's sitting on a desk. The gas particles will start to spread out. And remember, they're going in straight lines, but they're bouncing around other things too. So they're bouncing around. But eventually, those gases are going to spread slowly until they fill up the entire room. So they're going to be very concentrated at first when the person's close to it. It's supposed to be a person. Oh, stinks, right? They can smell them really, really close. And as you get further away, the smell gradually spreads over that way. But it's also less concentrated because there's a lot more air out there. Okay, that's diffusion. So we're going to put, they spread out and fill the room. And we usually think of that as a different kind of particle. We said gas particles will spread apart anyway, but you think of something that you can actually tell the difference. Maybe there's a different gas in there and it spreads out. Okay, now this last one. It's called effusion. Related to diffusion, but there's a difference. If you think of the fair. Oh, yeah, we love to think of the fair, right? Well, most years we do. So the fair, you get yourself a helium balloon. Okay, there we go. Holding on that balloon. Okay, hey. And so I'm holding on to the balloon, and I have it in my house. I don't know why I have the balloon in my house, but I let it go, and it floats to the ceiling. Woo! And it sits on the ceiling for like a day or two. But a few days later, I noticed that the balloon has gotten a little bit smaller, and it's starting to shrink. It's starting to fall a little bit too, right? And over my favorite part is when the balloon's just the only thing touching the ground is the string, and the balloon is kind of just sort of flopping around, but not very much buoyance left, right? Well, eventually then the balloon falls to the ground and it's all shriveled up. It's really weird looking, right? Because it's all stretched out, but the helium's gone. So first of all, let's say what we have there. Can I make this bigger? Can I move it? We have helium inside that balloon. Now, it's not all helium, but the majority of it's helium. Hee. Really funny. Okay, so now, also, this balloon is made out of latex. That's just a polymer, right? It's a polymer. The molecules are held together. just like an inner tube. There's another good example. I'll use my inner tube next. Okay. Now, latex, rubber, whatever that is, let me make sure I get the right eraser, the partial one. And make sure I get the right size. There, that'll work. Right? Latex, even though you can't see this, and even though it takes time, there are little teeny microscopic holes in that latex. There just is, right? Same as my bicycle tire, right? There's little microscopic holes in there. It holds air. I haven't pumped that tires up since 2 months ago, right? And now it's a lot lower. It still has gas in them, but they're a lot lower. And plus I ride it like all the time too. So there's these little holes. Now remember what's happening to these particles. They're bouncing. Let me see if I can get him. They're bouncing around, and they're all doing that, right? Now, helium's really small. So helium's small and light, and the holes are small. So what's going to happen? These heliums are small enough, if they hit it just right, boo, it can escape. Whoop. So they're bouncing around, hit a hole, boo, they escape. Oops, that one escaped underneath me. Whew, they escape. So what happens is those heliums can escape slowly. But the bigger molecules, say like the oxygen, and oxygen is actually O2, right? Because it's diatomic. The O2, that's supposed to be my O2, and maybe some carbon dioxide in there, right? They're big. So they're not moving as fast because we're talking about kinetic energy, right? They have a bigger mass, so they're moving a little bit slower. Plus, they're bigger. So just like if you're trying to you're trying to throw something into like a basketball hoop, or maybe you're playing cornhole or something like that, and you cut the hole smaller, right? It's going to be harder. Now, I'm not saying that it can't hit just perfect and maybe escape out. It probably could, but it's harder. It's not going to happen as easy. It's not going to happen as fast. The smaller molecules, lighter, moving faster, smaller, can go out the hole better, right? That's effusion. Okay, you're like, what are you talking about, Arnold? Well, here's what I'm talking about. Effusion. Gas escapes, or we can say diffuses, through a hole. Oops. I know you guys get mad every time I get my thing in the way here. So gas escapes or diffuses through a hole. It's effusion. Okay. So those are the 6 things that describe the nature of gases, right? All right. Real versus ideal. Remember, ideal was perfect. Real is not perfect. Right? When things happen for real, they're not going to work out exactly right every time because there's all sorts of little things that can go wrong. Same thing for gases. The things we're going to do are going to be close to what happens. But because of the way nature is and the imperfections and the randomness and the chaos, it's not going to be exact, but it's going to be close enough. And that's what we're doing in a lot of things. We're trying to be close as we can and still do the calculations. All right? I hope that makes sense. I'm not going to write anything down for that because I just replay that in your mind if you need it. Okay, now when I wrote this today, I knew exactly what I wanted to say about these things right here. And I will try to remember I put these things to give myself hints so I could tell you what I wanted to say. How can we measure gases? All right? So the first thing you need to do when you're measuring a gas, right? We want to know what? The number of particles. So what do we use for the number of particles? Well, let me switch my font. I'm going to switch colors too. We use our old reliable. Number of particles is the moles. So we're going to use moles to describe the amount of gas we have. But what can we do with moles? We can change moles into grams, right? And so this is going to allow us, that wasn't very pretty, but this is going to allow us to change the moles, the number of particles, into grams, and we can do that with our stoichiometry, which we already learned. Okay. The size of the container. We need to know the size of the container. I have nothing else to write about that, but remember, we can jam more gas in there, or we can have less compressed gas in there. It can be low density or a higher density, depending on how much you jam in there. And think about the bike tire. I'm going to get that pump in there. The tire's not going to change size, but the number of particles inside is going to change. And with the number of particles inside that change, the tire gets harder, right? Right? And so I'm skipping one because this is a little tie, and I didn't know how to my bike down here without a tie. I thought I'd do this in school, but I didn't have time today. Okay, so we're going to the next one. Squeezing particles together, right? And pulling particles apart. What do we do? What do we call that? We call that the pressure. So the pressure of the gas can change inside the container, and it's going to depend on the number of particles and how big the container is. So these things are all related, and so we have to know all these things before we know how much gas we have. For you guys who are keeping track, pressure equals the amount of force, and the force is the collisions, the pounding, the hitting, right? The force is the particles moving around. F equals ma. Particles are accelerating. As they hit something, they bounce off. That's the acceleration, stopping and bouncing back the other way. And they have mass. So the force they hit the side of the container with, or the side of the tire with, divided by the area of the tire or the bottle. Okay? So the pressure comes from the collisions. The force times the force, and then the area it hits, how big of the container it is. If you have a humongous container, you can have a lot more gas. You need to make the pressure. Okay. Speed of the particles. And speed of the particles, we kind of said this already, right, is related to the kinetic energy, which we already said it equals 1/2 mv squared. If you're doing your physics notes, I don't know. It's kinetic energy is 1/2 mv squared, and the most important thing is the velocity, right, or the speed. Oops. Let me get back to where I was. There we go. All right. So the velocity or the speed of the particles. Okay. I should have checked the time that I just did because I don't know how long I talked there. Oh, I talked for too long already. Okay, so that's a start for us today. We're not going to have any homework yet on this section because I haven't gotten to the good stuff yet. So that's a little introduction. I'll blame Franklin for that, for his 3 minutes slowing me down a little bit. But write these notes down. Make sure you have these notes down, and I will collect these notes then at the end of the chapter. Okay, so we'll just keep a running note, and that should be it. Hey, have a great evening, and I am out of here.